It is often assumed that the effective medium corresponding to a distribution of particles may be described as a homogeneous medium from the standpoint of coherent wave propagation, the homogenized equivalent having the effective dynamic properties of the composite. Here, we have used just this analogy to derive a dynamic model of the composite response. We obtain novel mathematical expressions for the effective parameters of two-dimensional metamaterial systems, having applications not only in electromagnetics but also in acoustics and elasticity.
So we've developed a more complete theory of homogenization. What do we mean by more complete here?
Well, we include higher diffraction orders in the model, which means we're not restricted anymore to the monopole and the dipole as previously.
So that means our theory is applicable to a wider range of frequencies than previous theories.
Indeed, the wavelength now can be comparable to the size of the inclusion.
It's also quite a general theory, isn't it? So it can apply to a variety of different wave types.
Yes, we derive a simple scalar problem in 2 dimensions, which means we can apply it to acoustic waves, that is sound waves in compressible fluids, or elastic waves in solids, antiplane elastic waves, and also electromagnetic waves of different polarizations.
And so that generality and that wider frequency range means that we can now use this theory to model quite a range of materials and wave interactions, a wider range than had previously been possible. So waves interacting in seismic waves with rocks, or acoustic waves with composite laminates, or electromagnetic waves with arrays of aerials. Or alternatively, I think it's important because it means that it opens up a different and new design space for people working on metamaterials, because now we've relaxed the restriction on the elements being smaller than the wavelength. So that could mean that larger objects could be within a metamaterial, which might make them easier to manufacture, for example.